Good afternoon, everybody. Tēnā koutou, tēnā koutou katoa. For those of you who don't know me, my name's Peter Berry and I'm Chief Executive of the Electricity Engineers Association. Welcome to the Future Networks webinar. It's the first webinar that we've run, so a very warm welcome to you all. This year, the EEA made the tough decision to cancel our conference due to COVID. And that's the first time we've cancelled one of our events since World War II. Went back and had a look. We cancelled it in 1941 and 43. So pretty big event occurring globally that meant we had to cancel our conference. Given the collaborative culture of the EEA, the high number and the very high quality of the abstracts offered for the conference, and the EEA desire to offer new ways of engaging with members and sharing knowledge, the EEA Asset Management Group agreed to host a series of technical webinars. We've partnered with the Epicentre at the University of Canterbury, and this is to provide an opportunity for our future engineers to engage with people within the industry and engage early on issues impacting on the industry. Over the coming months, we'll bring in other technical experts as part of our webinar program to partner the technical presentations. So welcome to the inaugural EEA Winter Webinar. I've got to say it's new for the EEA and we have our technology trainers on, so remember to be kind to us today. Can I just do a special shout out to Sean McCready. Sean did an awful lot of great work in terms of getting this webinar ready. There are a few mountains and hills to climb, but a big thank you to you, Sean, for the work that you did. The theme of the 2020 conference was engineering, technology and innovation in a low carbon environment. So we're building our webinars around a series of key issues that were identified as part of this conference. Today we're looking at the uptake of solar PV and the uptake of electric vehicles and what impact they will have on the networks. Today we have three organisations talking about what they are doing and how they are preparing for future networks. In Australia, 21% of homes have rooftop PV solar systems, and in New Zealand there's already 85 megawatts of distributed solar installed, and just over half of that has been installed in the last 2 years. Transpower's Te Māori Hiko report has modelled the mass solar scenario that could see household uptake of up to 50% by 2031. The costs and economics of solar is improving, and this will continue to drive the uptake and connection of solar PV into our networks. EV uptake in New Zealand is also growing. As at 2020, the New Zealand fleet size was 20,000. Compared to 1,000 4 years ago. And with registrations around 42 cars per month back in 2016, it's now close to 600 EVs being registered a year. Both these technologies will impact on the grid and impact on how networks will be operated, maintained and built in the future, and we need to be prepared. It is fantastic that the three presenters you're going to hear today are progressing planning for the future with the many unknowns that we face. The snowball of technology has left the top of the mountain, so let's get ready for what will be a challenging and interesting ride for our industry and our engineers. As I said, this is the first of 4 planned webinars, so please enjoy the presentation, take the learnings and insights from each of the presenters and their topic areas. If you have questions, you can type them in and send them through to us using the Microsoft Teams message facility. It's now my pleasure to ask Dave Brannigan, Chair of the EEA Asset Management Group and Infrastructure Lifecycle Manager at Orion, to introduce each of the presenters. Dave, over to you.
Thank you, Peter, for that. Hi everyone, my name's Dave Brannigan from Orion. I'm actually the network manager. Sorry about that, Sean, I should have updated that. There's someone far wiser doing the life cycle role now. I'd like to welcome you all this afternoon. Like we say, this is a new one for us. Looking forward to your feedback from it as well. But what we'll do is we'll kick on in, and it's my pleasure now to introduce Richard Kingsford from Wells Network. So Richard's got 20 years experience across the industry in both planning and operational roles. And in his current role, he must manage existing assets, the current environment, while understanding the impact of new technologies, changing landscape, and expectations. Working well brings the opportunity to forecast future network and DSO requirements, then use both technologies and cutting-edge technologies to address these requirements. So, Richard, over to you.
Hi there, everyone, and thanks very much. Thanks for setting the scene there, Peter, and thanks for the introduction, Dave. First, I have to apologise for the lighting here. I look like I'm in witness protection, and there's a little bit of light contrast with the shininess of my forehead. Not much I can do about that one. We'll start this PowerPoint, and someone will scream out at me if we can't see it. My mouse disappears. So today we're talking about Network Planning 2025, and I set the date 2025 because it's far enough into the future that it's achievable, but it's not that far. It's not that far at all. And in fact, if you remember this screenshot, if you're old enough to see this, you'll understand how quickly these dates can come upon you when something seems so far in the future, but yet it's right there. So the aim of this discussion is to provoke thought and intelligent discussion. So I'm going to throw some ideas out there, and they're thoughts that are in development, and we're in discussion on some of them. We haven't implemented some of them. Some of them may never be implemented, but the idea is to share some solutions and really focus on the solutions. There's been a lot of talk about the issues and the problems, and Peter's given a good summary of that, but I'd really like to think about what we could do and what we're planning to do to address those. Must give thanks to Well. They're a very progressive company, and they've invested in technology, and they do this to facilitate learning. They're on an aggressive path to DSO, and they've really invested in their people to understand these issues, and I'm very thankful to work here and to be able to partake in the learning opportunities. There's a small caveat in there around that some of these thoughts are my own, and while we're sharing them and we are discussion, and I certainly benefit from a lot of the information that comes from Well. I don't want to put them on the spot with anything that I present. So I'm being provocative with some of these ideas, so please take that in the intent that it is intended. Right, the plan. So we're going to look at network planning to allow for electric vehicles and photovoltaic cells. So I'm going to call them EVs, but let's just understand that in the context that I'm presenting here, they're going to be one and the same. The PV is going to push the belly of the duct curve lower, and the electric vehicles is going to pull the bill of the duct higher. And I'm really looking at the change in voltage, because there's been a lot of talk about energy, and that works at a high level, but at the distribution level, I think it's the change in voltage which is going to be so very important. And that's why I'll be focusing a little bit on impedance curves, and then what we're measuring with our smart meters, and what we're in the process of gaining measurements with our smart meters. Along with network solutions, there's always non-network solutions, and we'll touch on a few of those. And then for a completely new topic, we'll just talk about moving the N-1 closer to the customer and what can be done there and what opportunities that presents for us. So EV uptake. Peter's done a very good summary of this, but I just wanted to show this graph, and this is the non-aggressive graph. It's the base scenario. There is one that goes higher, but we're really looking at about 50% by 2040. Believe it or not, or whether it's going to be faster or slower, but it's very, very significant. And I'm not going to look beyond 2040 for this presentation, because I'm going to assume, rightly or wrongly, time will tell, but I'm going to assume that after 20 years, the early electric vehicles will be retired, and there'll be a cheap supply of batteries that I can use to mitigate the issues that further EVs present. So review that in 5 years, 10 years, but that's my assumption for now. Also, when we look at the problem, when we're looking at the past, we had the case where we had these incrementally increasing loads and they all looked very much the same. But in the future, we get these step loads. One EV, quite a step change. Same with a solar, and they tend to group themselves. It tends to be an affluence effect or even logistical of where EVs are the most advantageous. So these pose some problems to us. So in the past, we had our aggregated loads. We've now got the step changes. I'm going to suggest that in the past, it was very hard to measure the LV and what was going on. And I think it's quite possible, and we can demonstrate as really in the past, people have used modelling to determine solutions, and I'm going to suggest that modelling determines a budget, but measurement will determine our solution. We're going to use actuals. We'll see why in a minute. So first, just a couple of little almost facts. So one EV charging at the wrong ICP will require a significant network upgrade. So we have some portions of the network where one EV and that change in load is going to drive such a large change in voltage that we will have to make an upgrade. Second one, in a very, very simplistic sense, that a change in current multiplied by the impedance is going to give us a voltage change. So that brings us to our impedance curve. And this is our network to each ICP and the percentage of the network that is at that cumulative impedance. A couple of important little milestones in here, and they're a bit rounded, but we have 170 instances where we get about 0.4 ohms. And that means that a standard single phase EV charger is going to change my voltage by more than 5%. And then if I've got my 0.2, then I'm looking at two EVs that will be able to do that. Obviously that's two EVs in a similar, on the same phase, similar location. There's a lot of caveats on these things, but we roll through it pretty quick. You guys are all smart people. So these are some interesting numbers, and this is a real curve, but you've got to have fairly good data to get this out of GIS, and there's a few assumptions to go behind it. So you reserve the right to change the numbers in the future. But for now, they're going to give me a good ballpark. So if I change that into a risk scenario, when I'm looking at the percentage of my network transformers, and then the probability that we're going to have to make an upgrade. So basically using that impedance. And we've used our GIS data, but you could use the green grid information that's derived from similar sources, both working on impedance. It's pretty good. We can see that this curve says that of this 10 or 20% of our transformers, they're definitely going to require an upgrade if they have two EV chargers on them. And then it tails away, and one is a similar curve. If we match that with the cost of every upgrade, and we should plan these in impedance again. So if we're close to that change in voltage, there might be a small section of line that we can improve, just a small section, a small cost, or we can manage the load, we can smooth it out. We can manage that load so that we don't need to make that upgrade. So a small cost here for these ones that are between 0.2 ohms and 0.4. But from there, anywhere up to 0.9, we're basically splitting the line and adding a transformer or something similar. It's more major. In this case, I've used 0.9 because if I have one transformer feeding from the end, if I split at 1/3 and then put a transformer halfway between the next 2/3, I get about 0.3 ohms, and I think I can manage. I'm back into the management zone. 50k is a bit light, but the numbers are quite scary, so I don't want to scare you too much. So I've gone with 50k for that transformer. Anything above 0.9, and we're doing multiple improvements. We definitely have some strings in our network where the LV does tee off perpendicular, and the cost is going to be more than this, and it's pretty scary. And that's where I've capped at 100k, because I'm going to say at that range we're probably a an off-grid type of non-network or a ICP support sort of solution at the ICP. So a few assumptions here that lead to this. So a 20-year budget. So if we have that uptake in EVs, and I'm looking for that 20-year budget, and I've got the number of instances where I'm between these impedance levels, I can derive a cost. And then if I take that cost and I take the EV uptake and I match those two, I can get a cost per year. And costs will vary and the positions will vary, but as a first ballpark to try and put a dollar value on how much EVs is going to cost, this is I think this is a reasonable start, and at least we've got a starting peg in the ground at which we can start to shift and start having some pegs in the ground that we can start to discuss and track and monitor and see how we're going as we go through this. But I can also give a good 20-year outlook to say, hey, in the next 20 years, we've got $11 to $15 million in here. Not 100 million, not 5 million, somewhere in between. And then interestingly, this is something that others could take on board and maybe regulators could look at, I suggest maybe. This is our network in the blue, but it could be another network that maybe has a lot more cabling or a lot shorter lengths of LV, and they may have an impedance curve that looks like this. And that's exactly half our network, by the way. And you can see that the impact of EVs on this network is drastically less. So by looking at these impedance curves for the percentage of the network, we can see how much compared to other costs within the network that EVs and PV is going to likely cost that network, potentially impact that network. Interestingly, when we're looking at impedance as well, the areas that have the highest impedance for us are the slightly rural areas just on the outside of Hamilton. So these are the rural areas that were extended. They've got light copper, 16mm copper for great lengths. They're also quite affluent people, quite wealthy people, and they're also in that sweet spot for an EV journey. Lots of savings for them to be made, and so likely to get it, and it's also likely to cost us money. So that's an interesting fact. The ones in the very rural areas tend to be 11 kV to a transformer and then a short LV, so they don't tend to have that much impedance. Something to note, and this would be an interesting curve to line up other EDBs and see where they sit. So just to recap, we've gone through network planning, we've looked at the impedance curves, but that was sort of the big bucket planning, and now we're going to look at what we would measure with our smart meters and what's possible. So above and beyond just energy, what we're also gaining the insight to look at in the next 6 months is the voltage distribution. And we'll be able to show this curve and how it shifts throughout a day, and for a ICP or for a transformer or for a higher aggregated load. But this would be a fairly standard, well-utilized transformer, moderate impedance, and the distribution across there for the voltages across at a transformer level. But if we look at two other curves, both displaying a low voltage, you can see that just by monitoring the voltage at the ICPs, I know that I can tap this blue transformer and I can address these low voltages, but there is nothing that I can do without further investment on this orange curve. Few companies in Melbourne and Australia are really well ahead in what they can do on this. And the voltage also allows us to measure impedance at the ICP level, and once we can measure impedance and we're measuring the change in our impedance, then we're really getting into some really sophisticated and intelligent network diagnosis. So it's a different topic, not this presentation, but certainly in the planning process, understanding this voltage distribution is really going to help you out. Knowing where the ICP that's getting the EV, where it's sitting on this curve, and how that changes through a day, a week, a month, a year. But hand in hand with those network planning decisions, we should be thinking about non-network solutions. And this is room to be developed, I think. Certainly my view is that in the past we had a base load and then we had the icing on top, which is our controlled load, thinking more hot water in this case. In the future, that firm control, that 100% control that I will turn you off right now, I think will get less. Others will argue, but I'm sort of thinking that absolute control, the hot water, because of gas heating or at the moment heating, this could get less, but this area that we can influence is going to grow. And this is the sort of Internet of Things or other signals where I'll send out maybe a price signal or an instruction or whatever it be, and I might get 50% of the people responding, or 20%, depending on how strong my signal is. So this could be spa pools, pool pumps, it could be a refrigerator, it could be throttling back a heat pump, or it could be throttling back an EV charger. In this case, it's influence. We want to, in my view, keep the control with the customer. They like to feel in control. They don't want to be bossed around, but they could be influenced. This is what we're trying to do. So what we're trying to do is overall lower the cost to serve customers electricity as a whole, as a nation. This is what we're looking for. So if I have one LV feeder with 2 EVs and one with solar on it, a lot of solar, so I've got high voltages on one side and low voltages on the other, I really want to aim at an ICP level, or at least an LV feeder level, where I change the load. So in this case, an aggregator is not going to work. It needs to be at the LV feeder level. And if I do that, then I can manage my voltages, and then I can offset future upgrades. And I could rattle this up through the network, even up to GXP level, where I might influence people to cut off for a short amount of time. And the signals down low need to be quite strong, but the signals at GXP level, where I don't have to influence such a large percentage of the population, can be quite weak. And I think we can build an interesting model in here. And there is a number of ways that we could be delivering these incentives. Dollars and price is one, and there's a whole lot of challenges to overcome if that was the way, but whatever we're doing in this realms, I would encourage people to think about how can we reduce the network assets that are deployed so that we can reduce the overall cost. So a little bit of a summary of that. So influencing consumption at an ICP level will lower network investment. And this must be customer centric and easy. People aren't going to wait till 11 PM and then start switching on dryers, but if they have a home automation system or an app, then they might do it, much more likely to do it. And the technology is really enabling this. And this is what we're aiming for. So this is that same diagram that we saw before, just zoomed in a little bit, but this is the probability that I'm going to have to make a network upgrade with 1 or 2 EV chargers. And if I can keep that change in current per ICP to less than 10 amps, then here's the impact. And that's a direct saving in costs. Whew, right, here we go. 18 minutes, got a couple of minutes here. So we're going to move on to moving the N-1 close to the customer. And it's a really quick topic here, just one slide. So Hamilton's in a growth situation. It still is. I still believe that COVID might give it a bit of a knock, but it's going to come back. It's uniquely placed. And when we have a 2 transformer zone substation A, the traditional method of increasing our N-1 supply is to add a 3rd transformer. And we have these radial feeds. But I think in the future we have this, what we call the twins model. And because of the growth, we have the opportunity to build these new twin substations about 5 kilometers away, and we treat them as an N-1 twin. We can do that if we get fast switching between the 2 subs. And in fact, if we create a ladder structure with the LV, you can imagine that no matter where you are in the LV, there's pretty much a feed to one sub or the other through one 11 kV feeder or another, with fiber and circuit breakers and protection at the 11 kV, this is achievable. The change in investment for us is an easier substation build in green fields. It allows for future growth in that direction. And in Hamilton at the moment, we are getting growth in the west in this, and we can implement this system. We've got it in the northwest, we have it in the northeast, and we have it in the south. The other growth cell is in the centre for us, and being able to shift across the 11 kV out to these zone substations can relieve and upgrade and prevent us having to upgrade in situations where we don't have room, and we can't do those upgrades very easily. And this is a much cheaper and much more efficacious solution. We can deliver the N-1 down lower to the customer where it really counts, where they're really going to notice. So, bit of a conclusion, bit of a summary. Encourage you to plan your budgets on aggregated figures, but execute upgrades of measured values. I think we're the traditional approach of modeling. You'll have 1,000 different models, and the EV or the PV is going to arrive somewhere slightly different. And if we were to make these modeling and plan out these upgrades, we'll be investing before it's required and costing extra money. The second one is give customers the control. They really do want the control. As an EV owner, I really, when your EV doesn't charge it because there's a problem with the EV charger or something like that, it's super frustrating. It can really ruin your day quite quickly, and it's a black box mentality for the customer. So it really needs to work, and they really need to understand it. They need visibility, and they need to be able to influence. And if you're at home with a pregnant wife, you want that EV charged and ready to go, right? So you need some override, or you need some influence over what happens there. Should be considering impedance when we do our design. So when we're suggesting what upgrade, look at the impedance. Don't just make the smallest jump. Maybe the best solution to meet 2 or 3 EVs in the future is to chop the LV line and put in a new transformer. And the last one is to consider moving the N-1 closer to the customer. So I hope that that's provoked a few intelligent conversations and we can have a talk about it. It's a pity we don't have a happy hour straight after this. But that's what this was really about, is to provoke some conversations, and so we can start to get the wise minds out there to start developing and designing our future. Thanks very much.
Thanks for that, Richard. Yeah, look, mentioning the elephant in the room, voltage is it. It'll be the one that catches. It's either going to be depressed or it's going to exceed. We've got one question that's come in through that, and it was, what size kilowatt EV charger were you assuming with part of your studies?
7.2. So 32 amp is the one that's commonly out there. So the numbers are slightly rounded, but 7 kilowatts ends up being about 30 amps, which with an impedance of 0.375 ends up being 5% voltage change. You'll probably, this is where you come back to measurement, because our GIS, although it is very, very good, I must say, compared to others, we have a light of GIS in there that says light conductor or other things. And when you get light conducting or 16 mil copper, your impedance goes up quite quickly per meter. But if you go out there and you find it's 25, you might not have a problem. So it really does rely on having a bit of data or gathering that data over time. That's probably more going to impact you more than whether you're looking at 6 kilowatts or 7 or it's ramped back. But it's we're talking about the ones that you would install on a wall rather than the plug-in 2.5 kilowatt chargers.
Fantastic. Thank you very much. Okay, we've got Ewan McGill up next. So Ewan's a PhD student at the Epicenter, and he's with the Green Grid Project, and he completed a Master of Engineering in Electrical and Electronic Engineering with international study with distinction at the University in Glasgow in Scotland. Sorry, Ewan, I can't pronounce that name. So I'm going to hand over to you now. All the best.
Hi everyone, my name is Ewan McGill, and today I'm going to be discussing a stochastic method for assessing electric vehicle hosting capacity in low voltage distribution networks. EV uptake is accelerating both globally and in New Zealand. Electric vehicle charging increases load in LV distribution networks, and in the future these networks may become constrained by operational limits for voltage, conductor loading and transformer loading. In this presentation, I'm going to focus on network voltages. Network voltages can be assessed by performing load flow simulations. Because customer level loads are highly uncertain, a stochastic approach is suitable for load modeling. With a stochastic approach, loads are described statistically. Load flow simulations are then performed repetitively using what is known as a Monte Carlo simulation. Rather than producing a single result, the Monte Carlo simulation produces a distribution of possible results. The question is then, how can we interpret these results in order to make meaningful conclusions regarding EV hosting capacity? This is hopefully what I'll try and address over the next 20 or so minutes. I'm going to start off today by providing a brief description of the stochastic load flow simulation. Then I will discuss the steady state voltage limits in New Zealand, as well as how these compare to those used in Europe. Using the results produced by the simulation, I will then demonstrate how EV hosting capacity is assessed using both the New Zealand voltage limits as well as a possible alternative. I will conclude by providing a summary of the key findings. Okay, so let's start with the stochastic load flow simulation. The simulation is based on a model of a typical residential network. The simulation has a time horizon of 1 week and a temporal resolution of 30 minutes. A total of 11 EV penetration levels were assessed, and these are 0%, 10%, 20%, and so on up until 100% penetration level. The simulation uses a stochastic model for both the residential and EV load and is repeated using a Monte Carlo framework. The figure on the right here shows the topology of the network which was modelled. This network was identified from previous research at the University of Canterbury and provides a highly typical residential network. It has a total of 71 connections and contains a mixture of overhead lines and underground cables. These are indicated in solid and dashed lines respectively. The different colours represent different conductor types, as indicated by the legend below the network there. For some reason the shades are a little bit off, but hopefully you should still be able to identify the different conductor types there. Finally, the transformer provides a secondary voltage of 415 volts, which is of course a little higher than 1 per unit. So, as I previously mentioned, the simulation uses a stochastic model for both the residential and EV load. Residential loads are sampled from a smart meter dataset containing 400 average-sized households. The data has half-hourly resolution and comes from the week containing the annual peak that year. While residential load is modelled using measured data, the electric vehicle load is modelled using a mathematical model. The model has 7 stochastic variables. These are the arrival and departure times, the daily distance travelled, charger rating, battery capacity, charging strategy, and range anxiety. So, as an example, let's consider the daily distance travelled. For each electric vehicle in the network, the daily distance travelled is sampled from the distribution seen here. The x-axis shows the daily distance travelled and the y-axis shows the corresponding probability. The distribution is based on data from the New Zealand Ministry of Transport. It is not only the daily distance travelled. For each EV, all 7 stochastic variables are sampled from a corresponding statistical distribution, and this allows the diverse range of EV charging behaviours to be captured by the EV load model. Okay, so yeah, let's now look at the steady state voltage limits in New Zealand. In New Zealand, the steady state voltage limits are defined in the Electricity Safety Regulations Part 3, Clause 28, I believe, and these state that the calculated or measured voltage at the point of supply must be A, at standard low voltage, and B, except for momentary fluctuations, be kept within 6% of that voltage. Although the exact definition of momentary is ambiguous, these limits are relatively strict, as they require that all voltages are kept within plus or minus 6% during all of the time. These can be contrasted with the European limits, which are defined in EN 50160, clause 4.3.2. These state that during each period of 1 week, 95% of voltages at the point of supply shall be within plus or minus 10% of nominal, and all voltages at the point of supply shall be within plus 10% minus 15% of nominal. And it explicitly states that these are based on 10-minute averaged RMS voltages. There are 3 main differences between these and the limits used in New Zealand. Firstly, the tolerance is wider, extending to plus or minus 10%. Secondly, momentary is explicitly defined. And thirdly, there is an allowance for a small number of minor undervoltages while rejecting large undervoltages even when infrequent. In the following slides, I'm going to demonstrate how EV hosting capacity can be assessed using both the current New Zealand voltage limits and also a possible alternative, which, like the European limits, considers both magnitude and duration. Okay, so let's start by considering the New Zealand voltage limits. As I previously mentioned, these require that all voltages are within plus or minus 6% during all of the time. What I've shown here is a plot of the minimum weekly network voltage. The x-axis shows the EV penetration level, and at each penetration level, the box plot shows the distribution of results across all Monte Carlo repetitions. On each box plot, the central mark, or the notch, represents the 50th percentile, or P50. The lower edge of the box represents the 25th percentile, or P25, and the lower whisker represents the 5th percentile, or P5. There are points below the 5th percentile, but these are considered outliers and are not plotted. The dashed horizontal line at 0.94 per unit indicates the lower bound of the New Zealand steady state voltage limits. We can see that the level of the box plots decrease as the EV penetration level increases. We can also see that at each penetration level, there is a range of possible results. And this is because some repetitions produce more extreme results than others due to temporal coincidence and load placement. The percentage of each box plot, which is below the dashed line, provides the voltage constraint probability. On the graph to the right, the voltage constraint probability is plotted as a function of the EV penetration level. It can be seen that as the EV penetration level increases, so does the voltage constraint probability. So I've tried to highlight this with a few little graphics here. So we can see here the percentage of the box plot below the dashed horizontal line, and also the corresponding voltage constraint probability. And we can see that as we move up through the EV penetration levels, this percentage, and therefore the voltage constraint probability, increases. Let's do that a couple more times, so hopefully you can see that a lot more clearly. It's worth noting that even at the 0% penetration level, there is a small chance of a voltage constraint. This is when temporal coincidence is high and load placements result in significant phase or feeder imbalance. On the other hand, at the 100% penetration level, almost all repetitions produce a voltage constraint. The EV hosting capacity is defined as the maximum penetration level which can be achieved before the network becomes constrained. The simulation produces a distribution of possible hosting capacities because of the stochastic inputs. Here we will consider the 50th, 25th and 5th percentile hosting capacities. As an example, let's first consider the 50th percentile. The 50th percentile hosting capacity can be calculated by drawing a line which connects the P50 values on each box plot, as can be seen now. The first constraint occurs at the 50% penetration level, and therefore the 50th percentile hosting capacity is 40%. That is one penetration level below the point at which the first constraint is observed. Similarly, the 25th percentile hosting capacity can be calculated by drawing a line which connects the P25 values on each box plot, and I've shown that here in the blue. Here we can see that the first constraint occurs at the 30% penetration level, and therefore the 25th percentile hosting capacity is 20%. And finally, the 5th percentile hosting capacity can be calculated by drawing a line which connects the P5 values on each box plot. And here, the first constraint occurs at the 10% penetration level, and therefore the 5th percentile hosting capacity is 0%. The percentile hosting capacities can be seen in the table to the right. The P50 provides the expected hosting capacity. It's worth noting that when compared to the 25th and 5th percentiles, the P50 provides a relatively optimistic hosting capacity. That is, if you compare 40% to 20 and 0% respectively. It's worth noting, however, that when using the P50 hosting capacity, there is a higher probability of a constraint occurring at the assigned hosting capacity. If hosting capacities are assigned using the P50, it is therefore possible that penalties may be incurred in the future. On the other end of the spectrum, the P5 provides a relatively pessimistic hosting capacity. However, there's a significantly lower probability of a constraint occurring at the assigned hosting capacity. If hosting capacities are assigned using the P5, it's possible that networks may be reinforced prematurely and thus costs passed on to customers. These results demonstrate the strictness of the steady state voltage limits used in New Zealand. That is, that all voltages must be within plus or minus 6% during all of the time. Even at the 0% penetration level, there is a chance, albeit a very small one, that a voltage violation will occur. In reality, customer loads should be able to tolerate a small number of minor undervoltages. Shown here is a plot of the number of undervoltage hours per week for the worst affected customer in the network. Again, the x-axis shows the EV penetration level. At each penetration level, the box plot shows the distribution of results across all Monte Carlo repetitions. The right-hand side box plot is the number of hours below the 0.94 per unit threshold. The left-hand side box plot is the number of hours below the 0.9 per unit threshold. It can be seen that higher numbers of undervoltage hours are more likely at higher penetration levels. Furthermore, minor undervoltages, that is those less than 0.94 per unit, are significantly more common than major undervoltages, that is those less than 0.9 per unit. Here, we propose alternative steady-state voltage limits, where for each undervoltage magnitude threshold, there is an associated duration threshold. The duration threshold defines the maximum number of hours below the respective magnitude threshold. As an example, consider the thresholds seen here in the table to the right. These thresholds can be interpreted as follows. For the worst case customer, the voltage will not be less than 0.94 per unit for more than 5 hours during a week and will not be less than 0.9 per unit for any hours during the week. These thresholds are also shown on the plot now to the left. What I've shown here are the voltage constraint probabilities using both the New Zealand voltage limits and the proposed alternatives. When using the New Zealand voltage limits, there is a small chance of a voltage constraint even at the 0% penetration level. Furthermore, the voltage constraint probability increases significantly as the EV penetration level increases. So that's the New Zealand voltage limits as seen there on the left. When using the alternative voltage limits, the probability of a voltage constraint at the 0% penetration level is negligible. And the voltage constraint probability increases only marginally until relatively high penetration levels. The table shown here provides a comparison of the hosting capacities assessed using both the New Zealand voltage limits and the proposed alternative. When using the New Zealand voltage limits, EV hosting capacities are generally conservative. The only way of increasing the EV hosting capacity is by selecting a higher percentile value. However, in doing so, the probability of a constraint occurring at the assigned hosting capacity is increased. By adopting the alternative limits, EV hosting capacity can be increased without compromising on confidence. So we can see if we use the most conservative hosting capacity, that is the P5 value, when using the New Zealand limits, the hosting capacity is 0%, i.e. the network can't accommodate any EVs. Whereas if we move to the alternative limits, even when using the P5, the hosting capacity is now 50%. These alternative limits are still customer centric because they're based on the worst affected customer during the peak load week of the year. However, it is worth noting that establishing appropriate magnitude and duration thresholds should be an area of future discussion. Okay, so that is just about it from me. I will now just provide a quick summary of the key points. We have seen that a stochastic approach is required because loads are uncertain. And as a result, EV hosting capacity is also uncertain. When dealing with probabilistic results, choosing a high percentile value provides an optimistic hosting capacity, but this results in a higher probability of a constraint occurring at the assigned hosting capacity. On the other hand, choosing a low percentile value provides a pessimistic hosting capacity, but results in a lower probability of a constraint at the assigned hosting capacity. These results show that perhaps the steady-state voltage limits in New Zealand are a little too strict. Alternative voltage limits were proposed which consider both the magnitude and duration of undervoltage events. These allow EV hosting capacity to be increased without compromising on confidence. The alternative limits are still customer-centric because they are based on the worst affected customer in the network and during the week of the year with the peak load. We also recognise that future discussion will be required to establish what are the most appropriate magnitude and duration thresholds in order to maintain a quality of supply for all customers. Thanks to all our members and for everyone listening. If you've got any questions, just fire them away and I'll do my best to answer. Thank you very much. Bye-bye.
Fantastic, thanks for that, Ewan. What I'd like to do, introduce Peter Armstrong from Waipa Networks. So Peter's the network asset manager there. He has 28 years experience in the electricity sector, having worked in generation, transmission and distribution, as well as consulting in New Zealand and internationally. He holds a Bachelor of Engineering from the University of Canterbury and a Masters of Business Administration with distinction from the University of Waikato. So Peter, I'd like to hand over to you now.
Right, Tēnā koe everyone. Thanks for the opportunity to give this talk. I'll just skip back to first slide. So yeah, wanted to present a case study today of an innovation ecosystem with a couple of examples that Waipa Networks have been working on recently. So to give you an overview of my talk, just talk about the innovation challenge that Waipa Networks faces along with, I think, most electricity networks in New Zealand and internationally. And then we'll talk about the key concept, which is what an innovation ecosystem is. And with a couple of examples, one being a PV and battery system at a development on a network, and the other one in terms of facilitating EV uptake while managing the network peak load. Then we'll talk about some more detail about innovation incubators and accelerators, remaining relevant through innovation, and some things around transformation and what a transformational business model looks like. So this is the Waipa Networks distribution area. We face the same challenges that many distribution networks do in terms of having solar PV distributed generation, which is growing, albeit slowly at this point. We expect batteries, as they become more economic, to make customers on our network less reliant on our network, so they will begin to combine PV, solar and batteries and take less energy from our networks. And we also see the challenge probably more imminently of electric vehicles, both in terms of managing their charging impact on the network and the challenges that mobile loads have on shifting their demand around. So I want to talk now about what this key concept of the innovation ecosystem is. It's a useful framework for considering the role of components, which are supply chain participants, and complementers, which are external enablers, in assisting a focal firm to deliver their innovative product to customers by the above. So before I get into sort of more of the theory about that, let's just give you a mental picture of what an innovation ecosystem is. If you think about the Airbus A320 aircraft, so a large wide-body aircraft, and the technology development that was required in the airport infrastructure to allow the successful deployment. So you couldn't run an Airbus A320 until you had runways that were strong enough to handle it, and air bridges that were big enough to connect to it to get the passengers on and off, and all those sorts of things that you needed to do. So that's what an innovation ecosystem is you can't just bring a product to market without having these components and complementers to smooth their way. So a couple of academics, Adler and Kapoor, state that an innovation ecosystem is about explicitly linking the dynamics of value creation and the implications of value capture to the structure of interdependence in a firm's ecosystem. The perspective that we propose and test in this study exploits the relative location of activities within the ecosystem to distinguish among the different roles played by various actors in the firm's environment. We identify roles according to the location in which activities are bundled in the ecosystem by following the flow of inputs and outputs of firms, and use this as the basis of framework for an analysis. So a couple of points there under the key concept. So Adler's definition of ecosystems is structure. The ecosystem is defined by the alignment structure of the multilateral set of partners that are needed to interact in order for a focal value proposition to materialise. And Adler's definition of ecosystems is strategy. Ecosystem strategy is defined by the way in which a focal firm approaches the alignment of partners and secures its role in the competitive ecosystem. So Adler comments, if the heart of traditional strategy is the search for competitive advantage, the heart of an ecosystem strategy is the search for alignment. The value, rarity and immutability of resources finds its analogue in multilateral partnerships, and sustainably advantages much to do with maintaining relationships as it does with keeping its rivals at bay. So there's this concept around an innovation ecosystem that you're very reliant on the components and complementers within that same system to be able to achieve what you're trying to achieve. So this picture here is the the Lakewood development in the northern side of Cambridge town. And it's a significant network connection. It's about 1 megawatt of demand from a new hotel, an apartment complex, food and beverage and retail centre. Waipa Networks has arranged with the developer to reduce their contribution to the cost of the network connection in exchange for Waipa Networks obtaining the right to install PV panels and potentially in future a storage battery in the development. So the Lakewood Embedded Network is the first of its kind, approval having been obtained from the Electricity Authority to classify the transformers and LV network in the development as an embedded network belonging to Waipa Networks, who is also the parent network. This allows the electricity generated by the current 211 kilowatts of solar PV generation to be sold directly to the current 47 participating ICPs at Lakewood. Ultimately, up to 150 ICPs could participate and further PV panels could be added as the development is fully built out. So this diagram here is intended to show you what the innovation ecosystem looks like. So here we have in the middle, we have Waipa Networks as the focal firm in that blue box as the PV and battery provider. The components are listed out to the left. So we have PV supplier, a smart network in terms of the technology needed to manage this type of technology, a battery supplier, a control system if we have battery installed, and asset management and as an enterprise resource planning system. On the complements in the centre, we have the Lakewood developer as an important external partner to us. A home energy management control system would be useful for participants and ICPs within the development to align their consumption to periods when the solar was available. The transpouter system operator would be involved if we were going to bid the battery into the market for various services. EMH Trade, which is a company that does reconciliation and peer-to-peer retail, they're an important partner for us in terms of being able to reconcile the energy on the network and on the embedded network and to be able to sell the solar PV generation to the ICPs within the development who have opted to buy it. And the Waipa District Council is also a complementer in terms of getting building consents and permissions, etc. And at the end of this chain, the customer is a consumer of eco-electricity and a Lakewood consumer on that embedded network. So I've explained that detail in that first point in terms of the characteristics of the embedded network. Up to 356 kilowatts of PV will be installed on those roofs as we build out all the buildings in that development. So that's quite exciting. We've come to the conclusion that batteries are not yet economic, so we can add a battery easily at a later date, as long as with the addition of a control system, so we can manage the charging and discharging to achieve various revenue streams, whether that's storing the solar to be discharged for energy required after the sun goes down, or it might be to be offering market services in terms of reserve capacity and things like that. I just note there that we have a 100% PV subdivision called St Kilda on our network. That's because the developer there required by covenant all the houses to have at least 3 kilowatts of solar panel on the roof. We could integrate a community scale battery into that subdivision in the same way as that we're looking at this Lakewood development. That's a future opportunity that we could look at once batteries become economic. Now this table here looks at a matrix of outcomes for challenges to components and complementers. So when we have a situation here, when we have low challenges to components, external components and external complementers, so that's the top left hand box, we have just the internal focal firm innovation challenges for the organisation for systems, expertise and capital. So those internal challenges exist in all of these other boxes, so I won't talk about them anymore. I will move down to the bottom left, where we have an external constraint on the external components that might affect production. So not having economic battery supplies or control system integrations not being effective. Then move across to the bottom right-hand side. The external constraints would exist on both production and consumption. So it's a combination of both these other high boxes. Then I'll move to talk about the high constraint on the external complementers. So there'd be an external constraint on consumption, and so battery controls might be lacking. We can't load shift to match the PV production, or the trading system's not available for peer-to-peer trading. Now, in that last point, I do want to just emphasise the importance of EMH Trade as an external complementer to us in the Lakewood development, because they provide retailer and peer-to-peer trading services. So unfortunately, they've exited their position in the market of doing that, and so we don't have the ability anymore to operate the embedded network as we designed, and I guess that has reduced our margin in this particular development, which is unfortunate. So this illustrates the dependence that focal firms have on complementers if there are single providers or limited alternatives available. So we're looking for other parties who may be able to help us out with that, because it would help us realise, I guess, our full potential at Lakewood. Moving on to talk about another ecosystem example. This is for facilitating EV uptake while managing the network peak load. So in this case, the focal firm, again, Waipa Networks, our distribution network being available for EV charging. The components here are EV manufacturers and high and low capacity EV chargers. And the complementers are probably more important in this case in terms of electricity retailers passing through any price signals that we might have. So if we put, for example, time of use tariffs in place to signal when our peak load is and encourage people to charge their EVs off peak, we are dependent on electricity retailers passing those pricing signals through. That's really, really key. The home energy management system is another method of I guess, of the home EV charger being shifted into non-network peak periods, as is the charger control apps, where you could set up your car to charge every night, but it doesn't start until after 9:30 at night, something like that. And in terms of us gaining data to understand better how our particularly LV network is faring with the stress from EV charging, data from smart meters or demand management systems is quite important. And on the right hand side there, the customer is EV drivers, fleet or private vehicle car owners, and this whole system is intended to deliver good service to them. Right, so we'll move on to talk about innovation incubators and accelerators. So this is some input, I guess, from how the case studies that I'm putting forward from Waipa Networks compare to features of the UK innovation scene. So there's often interaction between corporates seeking solutions and startups developing those solutions is one feature that the UK innovation scene has. In this case, the example is how Waipa Networks engaged with EMH Trade. So they're a startup. They had this peer-to-peer reconciliation and trade of excess PV. So they are trying to match up PV owners who have got excess PV to sell during the day with consumers who want eco-electricity and will consume it at that same time. So we got in touch with EMH Trade through the Lightning Lab Accelerator, who were looking to I guess, shop solutions in the electricity sector. And we sought solutions for peer-to-peer retailing and reconciliation services for this Lakewood development when we got into discussions with EMH Trade. So there are some aspects of innovation remaining relevant that I'd like to talk about. I'm just giving credit here to Kystra Gibson, who's the director at Boehringer Partners in the UK, who came up with these. Aspect number one is to leverage strong relationships with enterprise customers. So in the electricity distribution network sphere, typically these are large users who may have a direct contractual relationship with the network, or their special needs for reliability or capacity means there is a non-contractual and direct relationship, since the retailer can't offer improved supply reliability or capacity. You have to go to the network for that. Aspect number 2 is to utilise information available that others don't possess. So the innovation on the network related to capacity for distributed generation or demand connection for industrial connections is a particular advantage of distribution networks. So we should make use of that to remain relevant. Aspect number 3, don't underestimate the value of making a personal relationship with customers. So in this case, getting permission for information use, for example, smart meter data or power quality information in order to be proactive on customer issues, customers may find it more acceptable for the distribution network to be asking for this information as opposed to their retailer, because we have an interposed relationship with them and perhaps we're less threatening. Aspect number 4, work together with other operators and industries. Electricity distribution networks should collaborate because we are natural monopolies within generally non-overlapping franchise areas. So it's a feature of our industry that means we should collaborate with one another more, and you do see examples of that happening. Now, further point on transformation and remaining relevant. The point that this slide is to make is that doing nothing in a changing environment comes at a cost. So if you look at the black line going through the centre, the assumed revenue from doing nothing is that things won't change and you'll still make the same amount of money. But in actual fact, the likely revenue is the red line. So if you do nothing, your revenue is likely to decline over time. So the smart choice in this situation is to invest in innovation, because your projected revenue will decline as a short-term cost, but over the longer term it pays off and into the future. So I guess the conclusion that we've come to is investment in readiness for emerging technology is an imperative to protect the future of Waipa Networks as a community-owned asset. Now I want to talk about a transformational business model. So Kavadis and Kostas Locke posed the question related to the transformational business model. They ask, no new technology can transform an industry unless a business model can link it to an emerging market need. How can you tell whether a model will succeed in doing that? So what they've proposed is a transformational business model that tests that. So here we can see there's some characteristics on the left, and what I've done is I've matched them up against the Lakewood pilot, which I was describing earlier, and we can see whether it is a transformational business model or not. So in terms of personalisation, it's not. It's a one-size-fits-all type thing. But the second characteristic, is it a closed loop process? Yes, it is. The process of PV batteries and consumers is a closed loop. Does it involve asset sharing? Yes, it does. So there's roof for the PV space, PV and space for the batteries and controls, which are shared assets between us and the developer. It does have usage-based pricing, which is typical, kilowatt hours. Is it a collaborative ecosystem? And I think the answer to that is yes. If you refer to the figure of the ecosystem that I was describing earlier, you can see that it is collaborative. And then does it involve an agile and adaptive organisation? So I think it's fair to say Waipa Networks is still on a journey to agility, but we have the advantage of being small, and we have rapidly adapted to some of these opportunities in the energy space that we've seen to do some innovation things. So that's encouraging. Right, so to wrap up with some conclusions, Waipa Networks is at the forefront of adapting to the innovation transformation that is impacting EDBs internationally. The application of the innovation ecosystem to two technology challenges shows the applicability of Adner and Kapoor's theory to international and New Zealand electricity sectors. Innovation incubators and accelerators are a useful engagement model between corporates and startups. and there are important lessons in remaining relevant through innovation, investing early, and learning how to apply the technology in a pilot sense that we should learn as an industry. And the Lakewood pilot is an example of a transformational business model as applied by leading innovation firms in the UK. So the process of comparing innovation practices in the United Kingdom to those being implemented at Waipa Networks has been very instructive and should inspire confidence in the innovation strategy being pursued as a strategic direction by the board and management of Waipa Networks. So just wanted to acknowledge Adam Fletcher and Kerry Watson, who have been instrumental in the Lakewood development and getting that off the ground. It's been a bit of a long road for them. And also to Dr. Thomas Sinaitis from the Waikato Management School at the University of Waikato. So the theoretical basis for this presentation was from a paper that he gave that I attended as part of my management MBA. So thanks to him. So yeah, if there's any questions, happy to take them.
Excellent, thank you very much, Peter. One question which I guess comes across all of them, can we get a copy of the presentation? So that would be quite good if we could do that. There was another one that popped up early on in your presentation with regards to, were you able to put the batteries and solar panels on your RAB?
Let me think about that. We didn't buy batteries, just to clarify that. The solar panels, no, and they're not part of our RAB. We needed to be quite careful that we weren't doing any cross-subsidisation between our lines business and our energy business. So we just needed to set up separate accounts for the PV investment at Lakewood, and that's the way it's treated. Yeah.
No worries. Thank you very much for that. I see now that under the published section that we have got some answers against those other questions, so hopefully everyone can see those. We have run a little bit over time, so I apologise for that. But I think that for a first go, this hasn't been too bad at all, so I'm going to tick that one off success. I haven't seen anything else come through yet, so what I'd like to do is just hand you all back to Peter Berry to sort of sign off what we've achieved here today. But thank you all to all the presenters. Do appreciate the effort that you've put in, and thank you for taking the time out to talk to us today. Peter, across to you.
Look, Dave, thanks very much for managing the speakers today. Thanks very much for Sean for organising this. To Richard, Ewan and Peter, thank you very much for your presentations. Certainly a lot to think about there. We're really at the start of some of these emerging technologies and new opportunities. But I think all three presentations really gave me, certainly, and I'm sure others, a lot to think about in terms of how it's going to impact upon them and their businesses. So thank you to the three of you. To the audience out there unseen, thank you for coming along today and participating, and thank you for the questions that came through. And just to remind you that we have another one of these in July. I wish I could remember the date, but I can't. But if you go onto the EEA website and have a look, you'll see that we've got our July winter webinar later towards the end of July. Look, if there's any feedback that you'd like to share with EEA, thoughts around other potential topic areas, areas that we can improve on, we'd certainly welcome those as feedback. But I'll now let everybody get back to their real job. Thank our three presenters. Thank Dave for his chairing of it. And again, thank Sean for his contribution. Stay safe and be kind, and we'll see you all again in a month's time. Thanks very much. See ya.